They wouldn't let me put my whole title on the slide. They said it was too long. I don't know what they're thinking about that. Now, hello. I wave at you. Some of you wave back. That's very kind. We're going to talk about a lot of strange things today. But we're not really talking about physics, even though it seems so. And so we're going to go through all of this, but my hope is that all of this will fit together to help us think about the future of learning, which is my goal. Now, I don't know how much you know about British literature, but there was an important poem that was written in 1922 called The Wasteland by T.S. Eliot. And Eliot was describing a world that was shattered. He described it as a heap of broken images. Because all of these structures, all of these systems that had been in place for generations were suddenly destroyed in a catastrophic world war. But the real transformation wasn't happening on a battlefield. It was something that was happening in classrooms around the world as people imagined a new way to understand the universe. Now, that vision of the universe had first been developed, that vision that we had had for so long was first developed by our friend Isaac Newton. And in Newton's idea, all we had to do was we had to take all of the universe and divide it into discrete chunks where everything fit and everything made sense. And if we could put everything where it was supposed to be, if we could slice up the world into thin enough slices, then we could understand everything. And Newton's formulae were about understanding discrete forces, splitting them up, and making them comprehensible for us. Now, the key here, if you're getting that kind of math feeling, is these things here. Because for Newton, everything could be determined. So, he described a world of regular order, a world that made sense, a world where forces acted upon one another, and if we just worked hard enough, and if we just explored everything, then we could understand the shape of the world. We could understand cause and effect, and everything would fall into place. So he developed, for example, the 3 laws of motion, of thermodynamics. And this vision of a world that could be understood and comprehended was powerful beyond the world just of science. So William Blake, for example, and if you've been to the British Library, you've seen a statue version of this very engraving, right? William Blake imagines Newton measuring out the universe and comprehending everything. But at the beginning of the 20th century, it turns out there was sort of a new sheriff in town. And what he began to describe was a world that was much more complicated, much more convoluted and strange, and that made a completely different sense of things. Because the world he described was a world where sometimes effect could precede cause, and where something like a vacuum was not empty because stuff would generate out of it automatically. Which is, of course, how we got the Big Bang. Bazinga. The problem was, even Einstein didn't like this world. It troubled him to think about a world where cause and effect were less related. So he chafed against it. He argued against it. He said, famously, God does not play dice with the universe, to which his friend Niels Bohr said, "Stop telling God what to do with his dice, Albert." Because you just had to follow the theory of things. And the world that he described, that world of relativism, of relativity, suggested that you could see things from one standpoint and they would be absolutely true. But if you stood in a slightly different place, you could see something fundamentally different, and both things could be true at the same time. And his famous formula was fascinating. You still see an equal signs there, but what he told us was that energy and matter were actually the same thing, which is kind of crazy, kind of surprising, because we'd always thought of those as very separate elements. And what happened was this universe of certainty and isolation, of splitting things into narrow, tiny little bits that Newton had introduced us to, got replaced with the world of quantum mechanics, a world of uncertainty and entanglement, of these kind of strange relationships between elements. So that our friend Werner Heisenberg, who developed this theory, this notion, the uncertainty principle, and that formula is even more exciting. And yes, if you're wondering, that is the Planck constant. But the thing I want you to pay attention to is this symbol in the middle. Because what Heisenberg told us, what he taught us, was that you could only look at one thing at a time. And if you looked at one thing, you couldn't know what was happening to the thing you were no longer looking at. So while you weren't looking, it might have changed. Erwin Schrödinger, who famously wondered about a cat in a box, introduced us to even a more strange theory. In fact, it was one so strange that Einstein called it spooky action at a distance. And what he said was something fascinating. If you introduce two particles to one another in a particular way, those particles become entangled. They change, they're connected to each other, they have a relationship. And even if you remove one far away from the other, they're still connected. And even if there's a bunch of stuff in the middle, they're still connected. And if one changes, the other one changes faster than the speed of light. Because effectively, those two parts have become one thing. They're entangled. They're connected to each other. Now, that shouldn't have been a surprise to anyone, because for most of human history, we lived in a world where you could not split one element out from another, where we recognized that everything was interconnected, that all of creation was entangled together, and we were entangled with it. And there were cultures that celebrated that, cultures that believed you had to teach children not just for the next generation, but for the seventh generation away from you, a generation who would never know who you were, who would never remember you. But of course, that Newtonian world meant that what we often did was we destroyed those worlds to civilize them. We destroyed those traditions to split things out into narrower and narrower groups. We forced people into a particular model of learning. And that model of learning has permeated most of the work that's been done in the world. So today, I don't really want to talk about physics, but what I do want to talk about, what I do want to think about is learning and how it works. And there are some things we know about learning. So there's a group in the US, the National Research Council. They do thoughtful work, so I assume my government is destroying that right now. That's not my fault. I apologize for the mayhem we're creating. And what the National Research Council said is very interesting, their research. And by the way, this book is available. I think every teacher should read at least the first 3 chapters of this book. Students come to the classroom with preconceptions about how the world works. If their initial understanding is not engaged, they may fail to grasp the new concepts and information that are taught, or they may learn them for the purposes of a test, but revert to their preconceptions outside the classroom. This is going to require some participation from you. Are you ready? It's very dark out there, really. Okay, so how many of you have ever had a science class of any sort? Oh, that's handy. All right, this part's going to be easy. All right, so let's imagine that I have a steel plate. I am going to heat that steel plate. I'm not going to melt it, but I'm going to heat that steel plate. And what I'm wondering is, what happens to the dimensions of that steel plate when I heat it? Does the plate get a little bit bigger? Does it get a little bit smaller? Or does it stay the same size? The plate gets bigger, right? I mean, this is kind of basic stuff, but the plate gets bigger. The reason it gets bigger, does anyone know? When we introduce heat to it, we are introducing energy to the system. And what happens is the molecules in there, they get more and more energized, and so they bounce off of each other with more force, and they push each other away. So when we heat it, it pushes out at all of the edges, right? It gets a little bit wider and a little bit longer and a little bit thicker. It pushes out everywhere because it gets less dense. Do you remember this vaguely from your school? All right, great. I am now going to put a hole in the center of that steel plate, and I am going to heat the steel plate again. And what I'm wondering is what happens to the circumference of that hole. Now, what I'd like to do to hold you accountable is you need to tell someone near you whether that hole gets bigger, gets smaller, or stays the same as the plate heats. Now, a rule, you cannot say more than bigger, smaller, or same, but you have to tell someone near you your guess. Are you ready? All right, go. All right, stop. Some of you are saying more than bigger or smaller or same. Cheating. That's cheating. The answer to this question is very, very important. So we'll talk about that later. In the meantime, what I'd like to talk about is this fellow called Derek Muller. Now, Derek Muller was a PhD student in physics at the University of Sydney, graduated in 2008, did his dissertation in 2008 on physics education. And what Muller looked at was the role of Khan Academy videos in learning about physics. Have you heard about Khan Academy? Great, an amazing resource. What he wanted to see was, are those videos efficacious in teaching and learning? So what he did was he got a bunch of people in, and he gave them a pretest on their understanding of basic physics concepts. And so he put them all together, he balanced them for a variety of factors, and then gave them this pretest. And on average, people scored 6 out of 22 in their understanding of basic physics concepts. And then he showed them Khan Academy videos about basic physics concepts, and he asked them, interestingly, how they felt about those videos. And people said, oh, they were really great, they were really easy to understand, I learned a lot, they were really helpful, I understand things a lot better now. And then he gave them a post-test. And how did they perform? 6.2 out of 22. It made no statistical difference in their understanding of physics. And the reason for it was exactly what the National Research Council described. Here's what he says. Students have existing ideas about scientific phenomena. If the video presents scientific concepts in a clear, well-illustrated way, students believe they are learning. But they do not engage with the media on a deep enough level to realize that what was presented differs from their prior knowledge. This came from Muller's research. He said there were 5 things that he saw happen as he was studying these learners. So first, they thought they knew it already. Because they thought they knew it, they did not pay, and this was the words of one of the research study participants, they do not pay utmost attention. Because they don't pay utmost attention, they don't recognize that what was presented differs from what they were already thinking. Because of that, they don't learn a thing. And here's the sort of cherry on top. They get more confident in the incorrect ideas they were thinking before. So what Muller did was he actually created a series of videos that started out exactly like the Khan Academy videos, but in the middle they slammed people into a problem. A conundrum, something they couldn't figure out. And he asked how people felt about those videos. It was really confusing, they were really frustrating, I didn't like it, I didn't learn anything from it. Those people scored 12 out of 22. Because the friction, the difficulty of having to think through an idea and make something with it, not just consume, but make something, is critically important, which is part of what the work we're trying to do at PyTop. What happens if you just get that information, you just consume it, you're not really doing anything with it? What happens when you make things is what's important. Which brings us back to this. So, can we have the house lights up a bit? Thank you very much. That was very fast. They're very efficient backstage. Well done. How many people think the hole stays the same size? Please raise your hands, be proud. A few of you. How many think the hole gets bigger? A few of you. How many people think the hole gets smaller? Most everyone. And it makes logical sense, right? Because it's pushing out at all the edges, and so as it pushes out at that center edge, it squeezes that hole down, and that hole... Hang on a minute, I was just thinking about something. If I had dots evenly spaced around that hole, and the hole was getting smaller there, would those dots be getting closer together or further apart? They would be getting closer together, which would mean they would be getting more dense. And if those weren't dots, but those were molecules, what that would mean is that the molecules would be getting more dense, but I thought you told me that when we heated things, they got less dense. So what happens to the hole? It gets bigger. Now, I thought, did you just lie to me about having science class? The problem is this. You went to a science class where you learned science concepts for a test, but you didn't learn to think like scientists. Now, let me say that what you demonstrated here today, most of you, the lion's share of you, what you demonstrated today was completely logical thinking. You said, it pushes out at the edges, that center hole is an edge, it's going to push out at that, which means that hole's going to get smaller. It's absolutely logical and absolutely wrong. I'm very disappointed in you. Fundamentally, but by the way, part of the problem is this. What if I had said not that there was a hole in the middle, but just a circle drawn in the middle of the plate? What would happen to a circle if you stretched it that way and that way? Would that circle get bigger or smaller? It makes complete sense. Well, of course it gets bigger. The hole is what tricked you up, because you were thinking too logically and you weren't thinking like scientists, which means you didn't really learn science. You just learned something for a test. And if most of what we learn in school is just something for a test, it does have an impact in the world. What we have to recognize is that knowing is this business we all say we're in, but knowing about a thing is not the same as knowing it. And that means learning about a thing is not the same as knowing, and that means learning about a thing is not learning. That kind of hollow learning has an impact, and it's not a positive one. Instead, why not harness all of that energy expended by so many students around the planet to solve real problems in the real world? And that's the question you've got to be asking everybody on this show floor. Because it turns out there is a convoluted path for learning, and yet it's the path that learning has always really taken. A path of iteration and discovery and failure and trial and exploration and making things. And we have to ask ourselves a couple of questions. If we can only measure and know one thing at a time, which our friend Heisenberg told us, then is what we're measuring really centrally important to learning? And if that's the case, I know a certain patent clerk who as a kid failed maths, who probably shouldn't have gone on to change the world. Mr. Einstein, you're just not performing well enough. And if the world around us is inherently generative, if the very nature of absence in quantum mechanics is that things explode into it, things create into it, then are we co-creating a matrix, a space, a framework in which learning engagement can happen? Or are we just going through empty repetition? What we have to do is not make that grid and stick all those students in, you fit here and you fit here, and split everything out and divide everything. What we have to do is build a multidimensional framework with spaces in it where people solve problems and make things and discover and create. And I can't tell them what that is. That's what they have to discover. I have to be helping them develop and discover their agency, their own power, not my power, not the things I tell them. That's part of what we've been thinking about on the learning team at PyTop, is how do we build a framework where everybody gets to make stuff and make stuff that solves real problems in their real lives, in their homes, in their communities, in their schools. Because if we can create a generation of makers, not another generation of consumers, a generation of makers, then we begin to solve some of the world's complex problems. This is not about being easy. This is about being hard. Because when it's difficult for us, when we experience that friction, just as Muller found out, when we experience that friction, it pushes us to the edge of our capability, and that's where growth happens. That's the critical piece. That's why we do complex things, and there are complex things we have to do. And those complex things, those wicked challenges, are not going to be solved by single people in single disciplines doing one thing at a time. They're going to be solved by a tangled collaboration of people from a variety of cultures who all understand things in diverse ways and who are all making something meaningful, doing their part to solve those challenges. What we need, in other words, is not another form of Newtonian learning. What we need is quantum learning, where all of the dimensions of learning, all the dimensions of the human experience, all the dimensions of culture and history, the dimensions of different groups come together, and where people make to change the world. What we have to create, in other words, are spaces, bubbles, holes, not presences. Don't fill it up with a bunch of stuff. It's so tempting on the show floor. It's tempting even when you come to our booth to think, oh, well, what we're going to do is just buy a bunch of stuff and we'll put it in there and we'll fill all those spaces up. No, what we have to do is create spaces that are empty where kids can create. And by kids, I guess I mean all of us. In the end, the thing we've discovered is that the world is full of energy. That the world is your new classroom. And if you're not preparing people eventually to move in the world, if you're not preparing your learners to move into the world now, and if they're not moving into the world now, you're doing them a disservice. That world is our classroom. That's where the learning has to happen. Thank you very much. Oh, I'm supposed to wait up here, I think. I forgot. Alas. I finished early. They're not ready for me backstage.
Great. It's really great that you finished early, Bill.
Yay!
Because we have a question for you.
You have a question for me, all right.
So Bett and Educate have partnered on a set of questions which support the dialogue between industry and education. So one of our questions for you is, how does your product make educators' lives easier? And I know you have a view on this, so I'm going to let you take the stage.
All right. Well, so I think the question about how anyone's product makes educators' lives easier is exactly the wrong question. Think about it. The way to make a librarian's life easier is for the books never to circulate and for no one to go into the library. That really makes the librarian's life easy. I don't have to reshelve. I don't have to do all this extra work. So I think the real question is, how should someone's product make educators' lives more engaging? And I think the way to do that, I think what we're trying to do at least, is we recognize that it's really hard to be engaging or to be engaged if everyone's doing exactly the same thing. There's no space for anyone to surprise me. And so I think the way to do it is to allow learners the agency to create. It's kind of what I talked about in the talk here. So what we have to do is not find products that are about ease or about simplicity. We have to find products that are about giving people a platform, making those spaces where they can bring their own views, their own understandings, where they can test things out and try them. Because we know from neuroscience that that's a richer kind of learning standpoint. So I guess what I would ask is, I would change that question to say what makes educators' lives more engaging. And I know for me, and I was in the classroom for 25 years, the thing that was most engaging was when my students made something that surprised me. And when I recognized that they were surpassing my own understanding, that they were doing something that I never would have thought of.
Sure.
And so that's, I think, the most powerful learning moment.
Great. That's brilliant. That's brilliant. It's almost taking them beyond the zone of proximal development.
Absolutely. I mean, that idea not only of Vygotsky, but LaVey and Wenger and their notion of communities of practice, right, where people move from the outside to the inside, that idea where people collaborate together. I mean, that's Vygotskyan as well. I think we've got to start thinking about all the lessons we've learned and really integrating them, not on a superficial level, but really finding those kinds of products and people who can help us enact that and really at a deep level. So I think that's exactly right.
Thank you.
Well
Thank
done.
you so much, Bill.
Yeah, thanks very much.
Yeah.
Okay.
Thank you for that, and thanks for sharing your ideas with us.
Thanks very much. Thanks, everyone.